Bismillahirrahmanirrahim. Dear students, as described during the lectures in sessional 1, that the linear data structures are divided into two categories, namely general list, in which arrays and linked lists were covered and discussed in detail. Next comes the restricted list, in which these tags and queues will be encountered and further explored. Dear listeners, the general lists allow the operation of insertion or deletion to be performed anywhere in the list. That is, the operations of update may be performed either at the beginning or in the middle or even at the end of the list. On the other hand, the restricted lists constrain the update operation either at one end of the list, such as the case of stack, or the update operation may be applied at both ends in case of a queue. Dear students, stack is a linear data structure that allows update operations only at one end, called top of stack or simply top. Stack inserts the element using push operation and deletes the element through pop operation. Stack exhibits the philosophy of LIFO. Stack is also called a pile or push down list. Dear viewers, as depicted in this diagram, this tag is also known as abstract data type or ADT when it is specified in terms of operations. It keeps or encapsulates the data and all operations on that data to be localized in one section of the program. The reason behind the use of stack is evident from this slide, as it states that the LIFO philosophy in stack postpones certain steps of processing until other conditions are met. Ladies and gentlemen, there are two types of stack, or simply stated, the stack is implemented in two ways. The static stack is implemented through arrays and has a fixed size. The static stack requires the maintenance of max stack variable containing maximum size of the stack. It also checks the overflow in case of push operation, whether the stack is full or the top is holding the maximum size of the stack. It also verifies the underflow in case of pop operation, whether the stack is empty or top is holding the null value. Dear viewers, depicted in this slide is the static stack implementation through array. This array contains two variables. First one is the top variable, which is the stack pointer, currently showing the position of the stack. The next variable is the max stack variable, which holds the maximum size of the stack. Dear students, in this slide, the algorithm of push procedure is shown. As you can see that the push operation checks the status of the stack, whether it is full or not, before insertion of any element is made. In this slide, the pop operation of the stack is exhibited. As you can see that the pop operation removes the data or the elements from the top of the stack, but before doing this, it also checks or verifies whether the stack is empty or not. Dear students, the dynamic stack with unlimited capacity can be implemented through linked lists The dynamic stack is free from the maintenance of max stack variable encountered in static stack. It is also free from checking the overflow condition during the push operation. Dear viewers, the dynamic stack is sketched in this slide containing the node top of the stack with info and link fields. Depicted here in this diagram is the push operation of a dynamic stack. As you can see that the top of stack node is maintained whenever the push operation is performed. The pop procedure of a dynamic stack is depicted in this diagram. From the diagram, it is also noticed that the top of stack node is also maintained as per pop procedure call. Ladies and gentlemen, the stack can be applied in many situations, from evaluating the arithmetic expressions to converting one numbering system into another form. It can also be deployed to sort a list through quicksort technique. The most common application of a stack is in the recursive function calls. Dear viewers, this slide exhibits three different forms of arithmetic notations, namely the infix notation, the prefix notation, also known as Polish notation, and finally the postfix notation, also called reverse Polish notation. In case of infix notation, the evaluation is made using precedence rules and priority policies set by the parentheses. On the other hand, the last two notations perform evaluation by the positions of the operators and the operands in the expression. The evaluation of arithmetic expressions is of two-folding process. At first, the expression is converted from infix to postfix notation, also known as reverse Polish notation. Then this postfix notation is further evaluated. The stack is used to accomplish the whole task. Dear students, this slide contains the algorithm to find the postfix expression P of the given infix expression Q. As you have noticed in this slide, that the algorithm passes these two parameters in its Polish function call. This slide provides the algorithm to evaluate the postfix expression P, which is obtained from the last algorithm in which the infix notation is converted into the postfix form. Dear students, another application in which a stack can be used is the quicksort technique. This technique applies the divide and conquer strategy, which further states that the problem of sorting a set is reduced to the problem of sorting two smaller sets. The quicksort technique deploys this stack during the sorting process. Ladies and gentlemen, the selection of the pivot in the quick sorting process has a major role in the success of this sorting technique. Initially, the decision of selecting a pivot is made by one of the three options. The popular choice is to use the first element of the given list as the pivot, although that may provide a poor partition if the input is pre-sorted or is in reverse order. A safe course is merely to choose the pivot randomly. The best choice of pivot would be the median of the array, which is hard to calculate and which slows down the quicksort process. Dear students, assuming that the number at the first position is selected randomly as the pivot, then the sorting process begins as follows. Starting with the number positioned last in the list, the scanning is applied from left to right, and scanning is stopped when the first number that has less value than the pivot is found. Swap the numbers. Notice that the pivot is positioned after being swapped where all the values on its right side are greater than the pivot. Again, scanning the new list from left to right, beginning from the position where number just swapped. Stopping with the first number that has greater value than the pivot, again interchanging the numbers and noticing that the pivot is positioned where all the values on its left side are less than this number. Dear students, repeating this process till the pivot is placed at the position where all the numbers on its right side are greater and all the numbers on its left side are less. This is the point where the placed number, that is the pivot, divides the list into two sublists after placing itself on the correct position. Repeatedly applying this whole process of sorting to the sublists as well will eventually result in the list being sorted. The slide depicts the algorithm to sort an array A with n elements using quicksort technique. The whole process of sorting a list using quicksort technique needs some parameters to be passed. These parameters are listed in this slide. Dear students, this slide formally provides the algorithm of quicksort technique. The whole process of quicksorting has already been mentioned in the previous slides. You are hereby advised to read and match this algorithm with the previously described details. Ladies and gentlemen, finally, the complexity of the quicksort technique is discussed in this last slide. The quicksort algorithm presents n² time complexity for worst case. This is due to the fact that the total cost of all the partitions would be at most n. The best case time complexity belongs to linear logarithmic class, which is n log n. And this is because of the fact that the two sublists are each exactly half the size of the original list. Last but not least, the average case time complexity also belongs to linear logarithmic efficiency class, which is n log n. To describe it exactly, it has 1.38 n log n time complexity. This is because of the fact that on the average, each reduction step of the algorithm produces two sublists. Dear students, in today's lecture, we have discussed the difference between the general list and the restricted list. We have discovered two data structures under the restricted list, namely the stag and the queue. We further explored in detail the stag, its component, and its push and pop operations. The application of stags are also explored in this lecture. The two-folding process of converting the infix expression into the postfix, and finally evaluating this postfix expression is also explained in today's lecture. The quicksort process is also discussed in detail and its complexity being discovered too. Finally, I hereby advise you to consult the 6th chapter of Data Structure and Algorithm by Lipschutz for further details and studies. Till the next lecture, stay home, keep learning.